So we're in section 6.4. And we're talking about the dot product. The second best way to multiply vectors. We'll get to another way to multiply vectors when we talk about three-dimensional vectors. So the dot product, you'll also see it called the scalar product. Or the inner product. The most common name for it, the one we'll use, is the dot product. So if we have our vector u equals u1, u2, we could also write that as u1 i hat plus u2 j hat. And we have another vector v, which is, we're going to say in component form, v1, v2. We could also write that v1 I hat plus v2 j hat. We write u dot v equals, nice and easy to find the dot product, u1 times v1 plus u2 times v2. Multiply the x components, multiply the y components, add them together. Now, one important thing to remember about the dot product is that the dot product is a scalar. That's one of the most common mistakes that students make with dot products, is that they want the dot product to be a vector. It's never a vector. So that's one reason it's called the scalar product. So when we find the dot product, when we multiply two vectors using the dot product, we get out a scalar. We'll talk about some properties of the dot product and talk about another way of thinking about the dot product in just a minute. But for now, what I want to do is just do a couple of examples calculating a dot product. So let's say we have u, v. We're going to have three vectors. U equals the vector 2, 6. V is the vector negative 1, 5. And W is the vector negative 3, 1. So we want to find u dot v. So we multiply the x components, 2 times negative 1. Add it to the y components, multiplied, 6 times 5. So I get negative 2 plus 30 equals 28. So the dot product of these two vectors is 28. For the next one, I want to do u dot v plus w. We'll do it this way first, and then we'll talk about another way that we could do this. So here we're going to do the vector 2, 6. And we're finding the dot product with v plus w. Well, v plus w is negative 1 plus negative 3 is negative 4. And 5 plus 1 is 6. So we're finding the dot product of these two vectors. So I just added v plus w here. And for this, multiply the x components. 2 times negative 4 is negative 8 plus 36. And this comes out to be 28 also. So calculating the dot product pretty easy. Multiply the x components, multiply the y components, add them together. Now what we're going to do in class, we're going to worry mainly about how to calculate dot products, kind of just working with the dot product. We're not going to talk about applications much for dot products. When you get into next year when you're in calculus, you'll do some applications of dot products. If you're in physics, you do applications with dot products. We use dot products to calculate work. We often use dot products to find distances between things in space, because dot products have to do with the lengths of vectors projected onto other vectors. So those are two big examples. Is we use the dot products for work and the dot product for distance. So that's a couple of applications that we use the dot product with. But what we're doing now is more just an introduction and just kind of manipulating the dot product. So any questions on how we calculate a dot product if we have our vectors in component form? All right, let's talk about some properties of dot products. A different way that we could do this last problem. So the properties, we just have a few properties of dot products that we need to know about. So for our properties, we're going to say that u, v, and w are vectors, and c is a scalar. So our first property, our order when we do our dot product doesn't matter. U dot v equals v dot w. When we talk about the other kind of vector multiplication, this property is not true. So we need to state it because it's not always true. So our dot product, we say our dot product commutes. The zero vector, dot any vector is 0. The last problem that we did, here's a different way that we can do it. U dot v plus w. We can distribute here. So the dot product has the distributive property. Yes, this should be v plus w. So we can distribute the dot product is distributive. So this would be u dot v plus u dot w. So we could have done that last problem this way and come up with the same answer. A scalar times our dot product. It doesn't matter where we do the multiplication by the scalar. So we could multiply u by the scalar first and then do the dot product, or we could multiply v by the scalar and do the dot product. So it doesn't matter which order we do the multiplication in, if we're multiplying by a scalar. And this last one comes up a lot when you start applying the dot product, this last property. If we take the dot product of a vector with itself, we get the square of the magnitude. And this property, again, this one comes up a lot when we start applying the dot product. For now, I want you to be aware that this property about the dot product is true.
So you fully solve it out, and then you solve for the magnitude.
Yep, they would be the same. So you said, what was the example you used, Daisy? 2, 6?
Well, yeah, we're using 2, 6 really.
So if we did 2, 6 dot 2, 6, here's the question that Daisy asked. 2, 6 dot 2, 6 is 4 plus 36, and the magnitude of 2, 6 is the square root of 2 squared plus 6 squared, or the square root of 4 plus 36. So this is that squared. So kind of nice the way it works out. And this quantity u dot u, or vector dot product dotted with itself, comes up when we're trying to solve problems with dot products, when we do applications. All right, questions on our properties? Yes. Oh, yes, thank you. That would be nice if we could just substitute any vector we wanted in. Thank you. All right. So let's talk about what the dot product tells us a little bit about the geometry of the dot product. What is it telling us about the vectors, how they're related to each other, if we sketch them out? So I'm going to say angle between two vectors. One way that we can think about the dot product, let me draw two vectors here. So here are my vectors u and v. And we have the angle between them, theta. And for this, we're saying that 0 is less than or equal to theta less than or equal to 180 degrees. So the angle between our two vectors is always between 0 and 180 degrees. So we're not talking about this angle out here. We're always talking about the smaller angle inside. We can show using the law of cosines. It's not particularly difficult. Let me draw one other vector here. Draw that one in blue. That vector would be u minus v. If I use the law of cosines on this triangle, the length of this side is the magnitude of u, the length of this side is magnitude of v, etc. This length of this is magnitude of u minus v. I can use the law of cosines. I have a side angle side triangle here, and I could actually I have a side triangle, and I'm solving for the angle. I can use the law of cosines on this triangle, and I can come up with cosine of theta equals u dot v over the magnitude of u times the magnitude of v. And that comes from applying the law of cosines to this triangle. I can rewrite this, multiply both sides of the equation by the magnitude of u times the magnitude of v, and I get another way of finding the dot product. U dot V equals the magnitude of U times the magnitude of V times the cosine of the angle between them. This doesn't require me to know the components of U and V. It only requires me to know the magnitude and the angle between them. So I don't need to know the components here to find my dot product. This gives us a way to find the dot product if we don't know the components of the vector. And also here, we can find the angle between the two vectors without knowing necessarily the components of the vectors. We can find their dot product if we know their dot product, and we can find their magnitude, we know the angles between them. So let's look at an example of finding the angle between two vectors, and then I want to talk about this formula just a little bit more. So let's say we want to find the angle between the vector negative 2, 3 and the vector 1, negative 5. So we want the angle between these vectors. Well, I'm going to use this formula, so I need to find U dot V and the magnitude of U and the magnitude of V. So U dot V, what is U dot V going to be here? I'll get it started. Negative 2 plus negative 15, and I get negative 17. So U dot V is negative 17. That's what I need for the numerator here. Magnitude of U. Is going to be the square root of 4 plus 9, or the square root of 13. The magnitude of V equals the square root of 1 plus 25, square root of 26. So the cosine of the angle between the two vectors is negative 17 over square root of 13 times the square root of 26. So the angle is the inverse cosine of this number. I can plug this into my calculator, calculate it all out, press the inverse cosine button, and I get that this is approximately equal to 131.8 degrees. So the angle between those vectors is about 131, almost 132 degrees. So kind of nice to be able to find the angle just from this. Saves a lot of work going through the geometry of finding that angle. Questions there? All right, one last thing to talk about. I want to talk about this formula a little more. So let's write that up again. U dot V equals the magnitude of U times the magnitude of V times the cosine of the angle between. What if theta equals 90 degrees? What's our dot product? Cosine of 90 is 0. If theta equals 90 degrees, u dot v equals 0. So the only way that we get u dot v equals 0, because the magnitude of u and the magnitude of v are always a positive number, the only way we get u dot v equals 0 is if there's a 90-degree angle between the two vectors. So what we say, the way we say that is, if u dot v equals 0, u and v are, we call it orthogonal. Orthogonal is the way we say perpendicular when we're talking about vectors. It's another word for perpendicular. So this is a way to test to see if two vectors are perpendicular. Find the dot product. If it's 0, the vectors are orthogonal. They make a 90-degree angle with each other. So this is a nice way to test whether or not vectors are orthogonal. Find the dot product. If it's 0, they're orthogonal. Special things happen, and we have special kinds of vectors that are always orthogonal. And we can, that's an important property to know about vectors, is if they're orthogonal. One example is if we're going around in a circle, the velocity vector is always orthogonal to the acceleration vector. So that's one example of a set of vectors that are always orthogonal, as long as we're going at the same speed. Uniform circular motion is one example. We can also get some other information about the vectors from the dot product. Because the magnitudes of u and v are always positive, so depending on whether the dot product is positive, negative, or 0 tells us how big the angle between the vectors is. Because the only thing that's going to make our dot product positive or negative is the cosine of the angle. So we're going to draw some pictures. So if u dot v is positive, our vectors look like this. The angle between them is acute. We already decided that if u dot v equals 0, u and v are orthogonal. And we know that the cosine of an obtuse angle is negative. So if u dot v is negative, then we have an obtuse angle. Because magnitude of u and magnitude of v are always positive. So the cosine is the only thing that would make it negative. A couple of other nice relationships. If u and v are in opposite directions, I'm going to say u dot v equals -1. Theta is 180 degrees. And I wrote these wrong. This isn't u dot v, this is cosine theta. If cosine theta is -1, then they're pointing in opposite directions. And if cosine theta equals 1, then they are in the same direction. They're parallel. So the dot product, the sign of the dot product, positive, negative, or 0, tells us the angle between them. If the cosine of the angle is -1, they are in the opposite directions, and if the cosine of the angle is 1, they are in the same direction. So just a couple of different ways that we can apply this idea of the dot product and the angle between them. Questions there? Okay. The homework tonight, mostly computing, calculating with dot products. There you go.